How Applications Speak, TCP and UDP Part 2. We're going to pick up right where we left off in the last nugget, which is we had just finished talking about TCP and UDP and going through Wireshark in all its glory, showing captures of communication with these two protocols, which was immensely valuable. Now I want to get back to some of the core principles, which is the common port numbers. That's where we left off, and then completing the end-to-end communication story. So we put all these pieces together and wrap up what I would call the network foundations. It's pretty hard for me after that last nugget to kind of jump into the ports because it just kind of bridges where that last nugget was at. So bear with me for a second. Remember that we have a computer, right, speaking to a server that is going to provide some service. Now, this server could be running web serving software. It could be running email serving software. It could be like Microsoft Exchange or maybe some kind of Linux-based email service. It could be running an FTP site to where it's sharing files. It could be running all three of them at the same time. The point of this is when we're using a protocol, namely these are all TCP-based protocols, when we're using a protocol to contact it, we need to specify which service we're looking for. And behind the scenes, our web browsers fill that in for us. So when we open a web browser, and actually I've already opened this Wikipedia page right here, but when I go to wikipedia.org, it automatically knows, I'm going to use port 80. As a matter of fact, I had this thought. I want to open up the Wireshark capture from the last nugget, and you can see behind the scenes, the computer's doing all this. It says, okay, destination port is port 80 or HTTP. Source port is 49885. So every single time you establish a session, so I've got this going, we'll say to the web services. So we'll have TCP port 80. It's always going to come from some source port that Windows just makes up. This is the dynamic port number. So it's usually going to be in the upper port numbers because all of the well-known ports are here at the bottom. Now do know, both protocols have 65,535 ports that are available for use that are distinct, meaning it's not like the TCP ports and UDP ports overlap. Port 53 on this side is different than port 53 on this side. They're two different. Of course, I would choose to circle the one that you're like, no, it's not. It's DNS. Well, one's a DNS server, one's a DNS client used for it's called zone transfers and stuff like that. But for instance, over here, port 80 is not HTTP. It's something else on the UDP side. So they are distinct 65,000 ports. Up to port 1023 is actually considered well known. And that's why I pulled up that Wikipedia page. I put some common ports here on the screen, but know that, this is just and it's like just this giant list of ports. Like, you can see right there, there's port 25 that's used for SMTP. That is an official standard like that. That is documented as RFC standards based. But you also see, we've got this WINS, which is a Microsoft service, which is unofficial. They run it on port 42, but they didn't create some kind of RFC standards because WINS is Microsoft proprietary. So you can go down this list. You find, I think they even have, let me just do a find, Warcraft. Yeah, look at this. TCP port 3723 used by Diablo, Warcraft, Starcraft. This is a cumulative list of well-known services that are out there, and you find all kinds of stuff. Microsoft Ants, for crying out loud, made the list. So you've got all of these different ports that based on. So let's say I'm running Microsoft Ants, which I'm really curious to see what that is now, and may just pause the video and go do that. It's going to go into the Microsoft Ants server, whatever that server does, manage the ants, I suppose, on port 4001. That's the well-known port for the Microsoft Ants game. Come on, you wanted me to click it, right? A free multi. Oh, I'm there. Anyway, so we've got these common TCP ports. Now, the reason I put these in a nice little bubble on the screen is these are ones that you will want to know, of course, if you're certifying, but for the real world in a huge way. The reason knowing these is so valuable is because it allows you to respond to needs a hand without running to a book or trying to remember these. I mean, and trust me, just you'll see these so often that you'll get them again and again. But of course, if you're studying for certification, boonk, bounce your head against the screen, memorize those guys. So the reason this is good, it's kind of like, okay, why is it good to know these? Well, remember, we've got all kinds of routers and these devices in between. It's very easy to turn a router into a firewall. Let's say, I'm like, my organization, our productivity is low because I walk around and I see people surfing the web all day long. I'm done with that. I'm going to immediately, and this is all it takes, I'm going to immediately block port 80 and port 443. I just go into this router and say, do not allow anybody except me, of course, to use port 80 or 443 to communicate on the web, and bam, you've just killed all internet access for your organization. It's I should say all web surfing access. Internet is a broad term, but let's say I don't want emails to go out. Block SMTP, simple mail transfer protocol, FTP, file transfer protocol. I don't want to allow take the opposite approach. I'm taking the negative side. Maybe it's the positive side. You know what? We're going to be running our own email server inside of our organization, and the internet is going to start sending us emails. Well, I need to allow port 25 inbound. Do you see the point? Like, knowing these ports is huge, not only for just day-to-day use, but if you're a firewall admin, that's a big part of what you do. So and let me just hit what these are. File transfer protocol, send and receive files. SSH, secure shell. That's essentially secure telnet, a way of accessing our Cisco devices and managing them securely, among many other things you can do with SSH. We have telnet, which is the unsecure way of managing your different devices. We have SMTP, which is simple mail transfer protocol, email. DNS server. Now, on the TCP side, this is used when you have two DNS servers. And he's like, I know everything about ants.com. I have all those records, and I want to replicate those to you so you know about ants.com as well. That's the DNS server side, port 53. You got HTTP. Enough said. POP3 is an email client. So if I'm sitting here on this PC, I can say I want to go download my email from a POP3 server. Now, I don't have it in the list because it's common, but it's not as common. But port 143 is actually IMAP. IMAP 4. Another way of email clients working. POP3 says, I'm going to download all of these onto my computer and most of the time delete them from the server. So it's all on my computer. If you're an Outlook whiz, that's where you create your PST files in Outlook. IMAP 4 says, I'm going to get my email, but I'm going to leave it on the server. As a matter of fact, I'm just going to be eyes looking at the server to tell me what email's on there. So IMAP 4 is a little better because you put your faith in the server staying online and not crashing, and not your own PC. Whereas POP3, if you lose your PC, you lose all your email. So that's just a bonus side note. And then we have, of course, 443 HTTPS secure web surfing. On the UDP side, we have a DNS client. We saw that tons in the last nugget, used for all those DNS lookups. And then we have port 69, which is used for trivial file transfer protocol. That is used all the time with, I'll say Cisco, but any network equipment vendor or IP telephony device. Essentially, the difference between these two, besides the one running on UDP and one running in TCP, is this one is secure. Secure in the sense that there's a username, there's a password, you have to log in. A lot of times you can restrict your permissions and all that. This one, no login required. You just kind of send and receive files. That's real easy. So I'll talk more about TFTP plenty because we'll be using it later on this series. But like firmware updates for Cisco devices, configuration, saving a configuration file, that's all done using TFTP. The last thing I want to do in this network foundations section is put all of these pieces together. I mean, the last four nuggets have really been dissecting and looking at all the different layers of the OSI model and the depth of functionality that they have, the IP protocol, ARP, and all of that. So I just want to take these puzzle pieces and assemble this landscape with them and say, okay, here's how they all fit together. So first off, I want to mention that I redrew this network diagram with a little more more real world. You might recognize this one from one of the previous nuggets, but previously I had, IP address, subnet mask, gateway, IP address, subnet mask, IP address, subnet mask. It just was really cluttered, right? It's actually not normal for a network diagram to do that, although you could. But what is normal is for people to just say, okay, this is the 172.30.100 network, like up to this first router, because the router ends the network, right? Is 172.30.100/24. Now that's class C subnet mask. So this represents the network. This represents the host. And then you can see all of the other ones, the network, what networks these are. Every single interface of the router represents a new network. And then they'll put the IP addresses on the devices. They'll say, okay, this guy is actually we'll say .100. This guy is .1. He's the default gateway. I'll flip colors. On this network, he's maybe .1 on this network, and he's .2, and over on this network we have .1 of 172.30.50.1, right? And then this server here is let's just make him .70 is his IP address. Okay. So this is our landscape, right? Now here's the scenario. This computer opens a web browser and types in http :/ 172.30.50.70, which is this web server over here. Now I'm taking DNS out of the picture. We're typing in the IP address manually instead of typing in www.something and letting DNS get involved, because there'd be too much to talk about if we did that. So we hit the enter key on our keyboard. What happens? Actually, you know what? If you are feeling like a stud or studette, pause right there, pull out a piece of paper, and write just a list of steps. Here's exactly what happens, Jeremy, when that happens. And then unpause and come back. Okay? Okay. So if you paused, welcome back. If not, here we go. So we've got this computer right here going to this web browser. First thing it does is go, wait a sec. That is not on my network. I'm looking at my network, 172.30.100. That is 172.30.50. Not me. So I know that I can't send an ARP message and just talk to that guy via a broadcast. I have to send an ARP message, and it's for my default gateway, this .1. So he sends an ARP, which is a broadcast message. Goes to everybody that's attached to that switch. They all ignore it except for the router, who says, "Oh, that's me, and what you're looking for is my MAC address." Now let's give these guys some quick MAC address information. Let me flip to a red. So his MAC address is 1111. He's 2222. Yeah, I know. They're 12 characters, but that's a lot of writing. So we're just plugging in MAC addresses all the way across the network. Okay, so this guy comes back and says, hey, my MAC address is actually 2222, and that's what you need to assemble your packet. So this guy says, okay, I'm going to assemble a packet. Now, here's the trick question. What's he sending? Well, remember, first time he's trying to talk to this guy, what's he going to send? HTTP. It's going to be a TCP-based protocol, and before we can do anything, we have to shake his hand. We have to do a three-way handshake. So what's in this packet? SYN. Synchronization bit. That's going to say, here's what sequence number I'm going to start at, and tell the other side, I want to start a session with you. Now, he starts encapsulating that packet. He says, okay, transport layer information. This is going to be from a source TCP port of 55511. Now, where did that come from? Well, Windows makes it up. It's a dynamically generated source port just for the session. The destination port, however, is well known. So I'll have destination TCP port of, what do you think? 80. He's using HTTP, right? So now the computer, Windows, is ready to receive back on port 55511, and he's sending to a destination port of 80. Okay. So from there, we have the source IP address, where we're coming from, 172.30.50. Wait a sec. Nope, not .50. I'm 100. I'm staring at the URL there. .100.100. That's so 100.100. That's our IP address, is our source IP. And then we've got our destination IP of 172.30.50.70. That's where we're going. Okay, so we're building this packet. We're encapsulating it with all the overhead needed to reach the other side of the network. Two more things that need to be added on there. One is going to be the source MAC, which in our case is 1111. And then finally, the destination MAC, which in our case is 2222. What it's saying is I'm going to use this router. I'm going to go to that router in order to reach this destination IP address of 50.70. Now, something I wouldn't expect you to know, and I haven't spoken about until now, but when you get down to this level of the data link, you're actually creating something technically called a frame. I'll talk about that in just a second, because at the very, very, very last thing it does before it's going to put this on the wire and send electric signals is it sticks a piece of information at the end of this packet. Some people call it the FCS. Some people call it the CRC. It's the same thing. It's the frame check sequence or cyclical redundancy check. Think of it this way. The hardware of the network card, almost every network card can do this built in. They've got chips to do it. Has like a little hashing blender. It's a mathematical formula where it takes that whole packet, throws it in the blender, and goes and spits out this little, it's called a hash. It's like a, we'll say 32 character, 115AB9C, blah, 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 blah. This giant hash that blending all this together in a mathematical formula generates, and it takes that hash and puts it right at the end of the packet. The packet goes all the way to the other side. And before the server really even processes and looks at that packet, it takes all this information right here, throws it in a blender, hits the same puree button. They've got the same mathematical formula, and spits out this answer right here, which it then compares to the frame check sequence sitting at the very end. If they match, he goes, great, this is a good packet. If they don't match, the server immediately drops it, because he says this is not a good packet. Either there's a malicious person that has gotten in the middle of me and this person and modified some data inside of there, or more likely there was just some kind of electromagnetic interference. I went by a fluorescent flickering light and it scrambled the packet, or somebody's chair rolled over the cable at just the wrong time. One of those kind of things. So it'll discard the packet. So this guy will send the message again. That's TCP. So that's what the frame check sequence is. And let me add one more piece of information. I said, I've been talking about this like a frame check sequence, a frame. There is actually technical language that people use for data at the bottom 4 layers. Up here's those top application layers, session, presentation, application. Those, that all happens in the computer. We don't care about them. But down here we have physical, data link, network, and transport. Technically speaking, you're supposed to call data different things as it passes through each layer. At the transport layer, you call it a segment. Like if you're talking about data being encapsulated there, you say, oh yeah, we have some segments being created. Or down here at the network layer, that's where you call it a packet. At the data link layer, you call it, I'm thinking it, but saying data link, a frame. And the reason, you look at it and you go, oh, I can see the reason I got that name, because I stick information on the front and end of the packet, thus the name frame. And then down here at the very bottom we have the physical layer where we have bits getting involved. So that's where we're saying, I'm sending bits on the wire. So technically, if you're a purist, and I haven't met many, you would say, okay, well, we've got frames going around the network, or if we're talking about physical infrastructure, we say, okay, well, the bits are being corrupted by blah, blah, blah. Like that's how you're supposed to refer to things. However, everybody nowadays calls everything a packet, just because it's really easy and you don't have to think. And I do the same thing. So everything going across the network is a packet. But technically, you're supposed to say, as the switch receives the frame. Did I say it was sent? Okay, the device sends it, right? So as the switch receives the frame, because it's a layer 2 device, it looks at the source MAC address, and I'll say, here's a bonus piece that we'll talk about later. If it has never heard of the source MAC address 1111 before, it learns it. And that's how it goes, oh, I didn't know that. 1111 is actually on port 5. Great, I'm now a little smarter. And then it goes, okay, destination MAC address 2222. He goes, oh, well, I learned about that. That's on port 9 over here. So I'm just going to switch that right over to this router at, and I'll say almost all switches nowadays are wire speed. So there's no delay at all coming into that switch. So the router receives it. Router looks at it and goes, oh, great, I've got mail. You've got mail. He looks and he goes, that's my MAC address. So he looks a little further and goes, oh, it's not going to me. It's going through me. It's going to 172.30.50.70, which is not me. So I am going to look at my routing table. And in the routing table, he's looking for a route to 172.30.50, not 70.0/24. Because routers don't really know about hosts. I mean, they can, but you don't want them to. They know how to reach networks. So in his routing table, he's going to say, oh, I remember, to get to the 172.30.50.0 network, that's this guy over here, I need to go to, where? 10.5.1.2. That's this guy. Wait a sec. Whoa. How did he know that? Well, because somebody had previously taken this series and had configured him to know that. They put in a static route or something and configured that device to know it, because it won't know it by default. That's your job as a Cisco person, is to configure it. So it's going to go, okay, well, to get to that IP address, which is him, to get to that IP address, I'm going to have to tear off the old source and destination MAC address and replace it. Now, the new source is going to be 3333. The new destination is going to be 4444, right? Put those in. Now, if it had to send an ARP message to figure out who that is, because he just knows the IP address, he would do that. However, most routers will have all that information cached. It'll have done it before at some point. So it then puts that packet, it puts the frame into bits on the wire and sends it over here to the router, who receives it, has the same immediate reaction. Oh, great, I've got mail, because this is my MAC address. And then he looks and he goes, no, that's not me. That's actually something connected to my LAN. That's fantastic. So he's going to send an ARP message, if he doesn't know already, to try and find the MAC address for this guy. This guy responds back and says, I'm 6666. He then fills in the new, again, crosses out the old, strips it off, and puts the new information on there. It's coming from 5555 going to 6666, and he just received a SYN. Again, I know we've done similar diagrams with less pieces like this before, but I have to say it again. We were doing Wireshark captures of this and seeing this all happen in what, like, from end to end, it would get there and back in 0.1, 0.2 second time frames. I mean, it's just crazy how fast all of this happens in between. So this guy realizes, oh, you want to talk to me. This is the first message of a three-way handshake. I see that your sequence number is going to begin at, it does, I know in the last nugget it was 0. We saw that in Wireshark, but it's not always that way. Let's say in the SYN message, he said, my starting sequence number is going to be 1000. I'll start sending from byte or number 1000. So this guy comes back and he'll generate, you want to remember? A SYNAC. He's going to generate a SYNAC, and it'll say, okay, well, I'm going to start sending data to you. I'll start from the number 500. And it's internal. Windows figures all that out of whatever sequence number he'll start from. And I'm going to send an acknowledgement that I received your starting point of 1000. So what's the acknowledgement going to be? 1001. It's always one more than the SYN. So, oh heavens, if I were to break it down every single time, same process, right? All the way back through. This guy says, okay, I've got the SYNAC. He does it one more time. He sends an ACK back, Jack, with the ACK number being 501. Like, I've received your SYN at 500. I know where you're going to start sending from. Now let's start sending. Now, after all of this, I've filled a screen full of information. Now he sends a request. The data, and so instead of a SYN, it would actually now be an HTTP. Most likely would be a GET message for HTTP, like give me your web page, whatever default web page that you're looking for. Unless you specified, I said I want index.htm or something like that. Then it would have HTTP GET index, .html. So that would be the actual data. Same thing all the way back here. Then sending back. As data begins to transmit, window sizes for TCP are increasing. Are you feeling this? Really, I mean, seriously, like I just reached the end of this, and right now, I know someone out there is like, oh, I get it. That makes total sense. Now, if it doesn't, if you're like, ooh, that was kind of no worries. I mean, it's great. Rewind, But I know that I just all those pieces that we've talked about in the last 4 nuggets all came together right there. So that is the complete end-to-end story of network communication. What did we see, and what do I want you to do with it? Well, we kind of put the lid on network foundations, seeing the common port numbers that you want to know, and I would definitely commit those, especially the TCP ones, to memory. And then we completed the end-to-end communication story, putting all layers 1 through 4 together in that big communication. So what do I want you to do with it? Well, number one, memorize those port numbers. You'll need them for the exam and for the real world. Second is use netstat. Use that netstat utility that I've been showing you a number of times to find out if you have a virus. I haven't said that until now. You're like, really? Yeah, go in and close everything down on your computer and type in netstat and press enter. And if you see like 50 or 100 different sessions that are open on there, that's not good usually. That means something's running in the background, maybe sending spam from your computer. It's a bot, you're infected, it's trying to attack or scan other devices. Now, I'm not saying if you see a bunch of stuff there, you're absolutely infected. I mean, people have all kinds of stuff. I mean, you got Dropbox running in the background, you got Pandora playing music, all that could be on this list, but I mean, seriously, that's a quick way. That's what I do whenever somebody's like, my computer's running slow. First thing I do is open netstat and see if there's some kind of weird stuff going on behind the scenes. Next thing I'd recommend you do, write it all down. If you haven't been taking notes, to rewind back to that end-to-end communication story and create your own little network diagram, or even better yet, envision it yourself. Go to a website on the internet, stare at it for a minute, and then say, okay, I'm going to draw up on paper how the communication for my house. I mean, use your IP addresses, use your ISP. Fill in all the gaps of your own picture of how you communicated that website. Then explain it all to a friend. That's absolutely the best way to learn something, if you can get somebody to sit down. Usually a spouse works well, or a pet. Then Wireshark. If you didn't do that in the last nugget, go to the last page of the internet. Remember I showed that to you? Go to the last page of the internet, real simple web page, and just capture that Wireshark data and analyze it. I hope this has been informative for you, and I'd like to thank you for viewing.